Very good morning, students. So today we will study a very important topic in your physical chemistry, very fundamental topic, that is solid state. Okay, so we will start solid state. You know the basic fundamental characteristic properties of solid. Solids are, correspond to very strong intermolecular force of attraction. Particles are held together tightly, and solids have high melting and boiling points. These are very hard, brittle, and have definite shape, geometry. And particularly, if you define a solid, that is the state of matter having melting point above room temperature, that is generally called a solid. And solids are very less compressibility in nature, having high density then compared to your liquid and gases you can compare. So these are few general characteristic properties, you might have gone through that. So the main key classification over I need to discuss over here, solid, that is solid basically are two types, that is one is crystalline solid and another one is amorphous solid. Crystalline solid and another one is amorphous solid. Let us discuss the properties or characteristics of these two types of solids. Very important from board point of view, difference between crystalline solid and amorphous solid. You see, so first of all, this crystalline solid have a regular arrangement or orderly arrangement of particles. Okay, so now two important categories of solid. First one, that is crystalline solid. Crystalline solid, and the next one, that is amorphous solid. Amorphous solid. First of all, a crystalline solid, this is it involves particles constituting particles are arranged in a regular fashion, in a regular manner, that is orderly fashion. Okay, orderly fashion. That means very arrangement. Suppose I am considering a crystalline solid, let's say A and B are its constituents. That means A, thereafter B, A, B, A, B, likewise. Okay, and here I can say B, A, B, A, B, A, A, B, A, B, A, B. So this is orderly arrangement, very regular fashion is there. Okay, so if I consider amorphous solid, that means particles are arranged in, it follows order fashion or regular manner. Particles are arranged in irregular manner. That means here the arrangement can be A, पता नहीं A के बाद कौन आएगा, let's say B, again A, B, very random arrangement. Okay, very random arrangement is there. B, so let's say here A, B, B, A, B, A, B, B. So very random arrangement is there. Arrangement is random arrangement of particles. random arrangement of particles. Okay, so here in crystalline solid, another important property of crystalline solid, that is crystalline solids are anisotropic in nature. Anisotropic in nature. While these amorphous solids are isotropic in nature. Okay, these are isotropic in nature. So iso means same. In chemistry, iso means same. Here you see, if you, what do you mean by anisotropic? There are some physical properties, okay, that is whose value varies in every direction. Okay, so that is the value of certain physical properties like refractive index, you can say refractive index, or resistance etc. varies in different direction. You see, since the arrangement is alternate in this case of crystalline solid, you see, suppose you proceed in this direction, let's say here you proceed this direction, the arrangement is A B. Okay, different arrangement. So if you proceed in this direction, the arrangement is something different. Here you see, if you proceed in this direction, that is the pattern is A B, and if you proceed in this direction, the pattern is A. So different arrangements you are getting in different directions. That's why the value of physical properties also varies with respect to respective directions. Is that okay? But no such case in case of amorphous solid. Since particles are randomly arranged, if you move in any direction, you can say, if you move in any direction, so no such variation you will get due to random arrangement. What we assume over here, that in every direction their values remain same. The value of physical properties, like refractive index, resistance, okay, remains same in different directions. This is called anisotropic and isotropic nature of amorphous and crystalline solids. Next point, these crystalline solids have very sharp melting point. The crystalline solids have very sharp melting point and a definite heat of fusion. Is that clear? So crystalline solids have definite heat of fusion and sharp melting point. But in case of amorphous solid, no sharp melting point is obtained over here. Okay, so amorphous solids correspond to no sharp melting point is there. No sharp melting point in case of amorphous solid. No sharp melting point. Okay, so if this can be confirmed from their cooling graph. If you consider here, that is temperature and this one is time, let's say. Here what happens, suppose I am considering the melting point of a solid. So if suppose a solid is here, this one is solid, so if you increase the temperature, then the graph will be like this. At this point, suppose this one is A, B, at B point, solid here, from A to B, this is solid. So from B, the melting of or the fusion of solid takes place until entire solid get converted into liquid. There we get a parallel line like this. There is no change in temperature in this. So this parallel line contains solid plus liquid. That means solids are getting converted into liquid. So at a point that is C here, all the solids get converted into liquid. Then further heating, the temperature of liquid increases. So here from C to D, that is liquid, and this temperature is known as your melting point. This one is called your melting point. Okay, so if you see this particular point is very sharp, you are getting a sharp melting point in case of a crystalline solid, because the particles are uniformly or regular arrangement, or they follows an arrangement of orderly fashion. So here this sharp melting point is very sharp. One question may arise over here, that you are heating but still the temperature is not changing there. Why? Because you know, in solid molecules, in case of solids, if you heat it, then energy is required to break the interaction of constituting particles. That is called latent heat of fusion. So the melting point is very sharp. In case of amorphous solid, you see no sharp melting point is there, since arrangement is not regular. Suppose this is time, temperature, and this one is time. So since arrangement is irregular, so you can get a curve like this. Okay, solid, you can get, it can melt over the all range of a temperature. That is in case of amorphous solid. Okay, so next difference, you can say these crystalline solids are called true solids, you know, because particles are held tightly and regular, and having a regular arrangement of particles, so this is called a true solid. But amorphous solids are somehow called super cooled liquids, or you can say pseudo solids. The amorphous solid is called pseudo solids, pseudo solid, or you can say super cold liquid, super cold liquid. And this super cold liquid is due to its fluidity behavior, okay, fluidity behavior. These are known as pseudo solids, and it is called true solids. True solid, crystalline solid is called true solid, and it follows long range order. The crystalline solid, it follows long range order. Long range order means the arrangement that is A, B, A, B, A, B. So this regular fashion, regular order is proceeds through a long time. So but this amorphous solid, particles are not regular, like A, B, again B, A, again A, again A, again B, likewise. So it is very short range order. Short range order, that means the arrangement varies point to point. Is that clear? So amorphous solid, you know, rubber, or you can consider glass, quartz, these are amorphous solids. And crystalline solids, you know, all metals, all the solids generally are crystalline in nature. These are known as true solids. Crystalline solids have sharp melting point and boiling point. Crystalline solids having a definite heat of fusion, and due to such regular arrangement, a very sharp piece is obtained in case of crystalline solid. Whenever you cut a crystalline solid through a knife, then a very sharp piece is obtained. But the irregular piece is obtained in case of amorphous solid due to irregular pattern of arrangement of particles. Okay, so very important. You know the characteristic of crystalline solid and your amorphous solid. Now let us discuss by considering the nature of particles, classification of solids. Classification of solids on the basis of types of constituting particles. So solids can be classified like, one is your ionic solid. Okay, so let me explain about ionic solid. The constituting particles are ions, oppositely charged ions. These are cations and anions. Then which type of force of attraction is responsible for this? You know, electrostatic force of attraction. Ions are held together by electrostatic force of attraction. And ionic solids are bad conductor of electricity in their solid state, but bad conductor do not conduct electricity in solid form. However, they conduct electricity in their molten state or fused state. Conduct electricity in fused or molten state. That clear? Example, this is NaCl, all ionic compounds, CaCl2, MgCl2, etc. Is that clear? Next type of solid, that is covalent, or this is called network solid. Here the constituent particles are atoms. Constituent particles are atoms which are held together by weak van der Waals forces of attraction. Okay. They are atoms are, as the name suggests, covalent. So definitely covalent interaction is there. So atoms are held by covalent bonds. These are called network solid. Because why? You see, for example, if I consider diamond. So in diamond, graphite, you can each carbon atom is tetrahedrally arranged like this. So here, so this is covalent or network type solid. Okay, so these ionic solids are very hard and rigid, but covalent solid little bit of less harder than that of ionic solids. So these are your covalent or network solid. Next, that type of solid, that is metallic solid. Definitely the constituting particles are metals, and metals are held, these are held, metal atoms. Okay, metal atoms are held by the sea of electrons. You see, these metal atoms are positively charged, Mn plus, positively charged metal ions. Okay, Mn plus. So the force which is responsible to hold these metal atoms, these are the sea of electrons. And surrounding the electrons are there. So positive, negative attraction is there. So they are held like this. And these metallic solids have high melting point, iron, nickel. These are your iron, nickel. These are gold. These are your metallic solids, and they conduct electricity in solid as well as molten state. They can conduct electricity. And next, the last category, that is your molecular solid. This is molecular solid. The constituting particles are molecules. Molecules are held together by weak van der Waals force of attraction. Is that clear? So this molecular solids, again, three types. One is polar solid. Next one is non-polar solid, and the third one, that is hydrogen bonded solid. That clear? So this polar solid means these are having polar molecules like HCl, SO2. So these are polar molecules. So in case of HCl, if you consider hydrochloric acid as a polar solid, how you see HCl, delta negative, delta positive, charge separation is there, and it behaves like a dipole. So this polar solid is due to the dipole interaction. Okay, here this is a non-polar solid. For example, I2. Non-polar solids means that is very weak London force of attraction is there. Is that clear? So iodine is a non-polar solid, and generally these are bad conductor of electricity. They do not conduct any electric current. And the hydrogen bonded solid. Both are the non-conductor of electricity, all these molecular solids. Is that clear? Next, hydrogen bonded solid, you can consider ice. Ice, water molecules are held by, okay, this dipole force, that is called hydrogen bond. So this is the structure of ice. So regarding the type of constituting particles, this can be the classification of your solid. Okay, so next we will discuss, that is, next we will discuss, since the crystalline solids are true solids and we are genuinely familiar with this in day-to-day life with crystalline solids mostly, so it's important to know the structure of crystalline solids, that is structure of crystalline solid. So first term, that is your space lattice. Space lattice. See, suppose I am drawing over here few points like this, and here like this. So if you join all these points, tell me, then you are getting a definite geometry over here. Okay, you are getting a definite geometry over here. This is hexagonal type structure. So space lattice is nothing but it is the arrangement of points in 3-dimensional space. Arrangement of points in 3-dimensional space. So if I define the space lattice, you can define space lattice like this. It is the very simple. It is the regular arrangement of points in 3-dimensional space. So that is called your space lattice. Okay, so if you just see over here, that is, if I doing like a diagram this, see, look at here, if I okay, let me do over here. You see, so if this entire cube, if I compare this entire cube as your space lattice, is that clear? And each occupying point, these are called your lattice points, where these positions can be occupied by atoms, ions, all these particles. So, and this smallest unit, this smallest cube, which get repeated over again and again to give the entire cubic space lattice. Okay, so this smallest cube, the smallest repeating portion is called your unit cell. Each constituting point is called lattice point, and the entire geometry is called space lattice. This is, if you join the lattice points through lines, then it will give you the geometry of space lattice. Is that clear? So 2 points you can write over here. That is the smallest repeating unit which repeated which repeated over again and again to give the entire space lattice is called a unit cell, and each occupying point, you can write, each occupying point is known as lattice point. Each occupying point is known as lattice point. That clear? So now let us discuss about the parameters of unit cell. That means the properties which define a unit cell. These are called parameters of unit cell. Parameters of unit cell. A unit cell is defined by edge lengths. One is edge lengths. These are designated by A, B, C along 3 coordinate axes, and interfacial angle along 3 coordinate axes. These are designated alpha, beta and gamma. Okay, so I can represent like these 2 parameters. Suppose you see this one is your x axis, this one is y axis, and this one is z axis. X, y, z. Okay, so if I do a cubical unit cell like this, here, see. So here this one A, B and C along 3 coordinate axes. These are edge lengths, and if I represent the interfacial angle, this is alpha, beta, and this one, that is gamma. These are the parameters of a unit cell which define an unit cell, and depending upon the variation of these interfacial angles and ABC, that is edge lengths, there exist 7 type of crystal systems or 7 type of crystal geometry there exist. Right now I am representing these 7 type of crystal systems. Okay, then you see these are the 7 basic crystal systems. Okay, and their edge lengths and interfacial angles are given to you. You see the 7 crystal systems are cubic, tetragonal, orthorhombic, rhombohedral, hexagonal, monoclinic, triclinic, and these are their edge lengths. In case of cubic, all are same. A is equal to B is equal to C, A is equal to B is not equal to C likewise, and these are interfacial angles, and due to their orientation in different directions, so there exist 14 Bravais lattices. You see cubic exist in 3 form. These are simple or primitive, body centered and ab centered. Is that clear? That's why 3 basic unit cells exhibit in case of cubic geometry, and 2, 4, 1, 1, 2, 1. So you can remember like 3, 2, 4, 1, 1, 2, 1. 3, 2, 4, 1, 1, 2, 1. Total that is 14 Bravais lattices. Okay, good. So in case of a cubic system, there exist 3 different unit cells. Okay, so in a cubic system, there are 3 different unit cells that I have told you just before now. The 3 are simple or primitive. One that is simple or primitive. The second one that is body centered, cubic, and the third one that is face centered cubic unit cell. Okay, so in simple or primitive, you can say particles are present at corners of the cube. Okay, so just imagine 4 spheres and below there 4 pairs. Okay, so this is simple or primitive. You can draw like this. This one is a cubic unit cell. Okay. You see, this one is cube, and simple or primitive, the particles are only present at the corners and each particles are touching to each other. So in a cube I am showing like this. This is simple or primitive. That clear? Particles are only present at corner. Next, body center. Particles are present at corners and at body center. Okay, so one particles are compulsorily present at corners like this. This is a simple cubic, simple or primitive, as I have mentioned over there. So this one is BCC. Particles are present not only at the corners but also at a body center. There is a particle at a body center. This is BCC. Okay. Next, F center cubic. Particles are present at corners including face center. Each face center. Okay. So here an FCC can be drawn like this. Particles are present at the corners as well as each face center. There are 6 faces. This is the structure of FCC. Is that clear? So let us calculate the number of effective atoms. Okay, number of effective atoms. How many effective atoms are present per unit cell? So that is designated by Z, or rank of unit cell. That means how many effective number of atoms present in a unit cell. So don't think that this unit cell having how many atoms, 1 2 3 4 5 6 7 8. No, it's not like that. If you imagine the space lattice, okay, so if I consider this particularly, its contribution will be how much per unit cell. You just see here, it is not only associated with this unit cell, because you know space lattice it is distributed 3 dimensionally. Here is also 1 unit cell, and in back side there is also 1 unit cell like this. Here also 1 unit cell. Okay, so this particle is associated with 1 2 3 4, and exactly the 4 unit cells also above 4 unit cells are present above. So above this layer, so this particular point is associated with how many cubes? 1 2 3 4 and 4 above 8. So its contribution, you tell me, per unit cell will be how much? 1 by 8. Okay, so particles contribution of a particle contribution at corner of a unit cell, that is 1 by 8. So in case of simple cubic, since particles are present only at the corners, so how many corners are there? You see 8 corners. So number of particles will be, so number of effective particles, effective number of atoms. So effective number of atoms, that is equal to 8 corner into 1 by 8, that will be 1. Only one particle is present in simple or primitive. Then here you tell me again. So this corner particle contribution 1 by 8, and the particle that is present at the center of the cube, its contribution is 1. Is that clear? So number of effective atoms of a FCC unit cell FCC unit cell, that will be here 8 into 1 by 8 particles contribution due to corner plus 1 presented center. So that will be 1 plus 1, that is equal to 2. So number of effective atom in a BCC, in a BC, sorry, this one is not FCC, BCC, that will be 2. That clear? So here Z is equal to 1, here Z is equal to 2. Now number of effective atom in FCC, okay, number of effective atom in FCC, that will be, in case of FCC, you see the particle present at a corner, how many contribution, how much, 1 by 8, I have to explain it. And here you see the particle that is present at face center, it is contributed by another unit cell also present over it, you see. So this face center particle, it is contributed by 2 unit cell, so its contribution towards 1 unit cell, that will be 1 by 2. So how many phases are there? 6 phases. So particles due to corner, that can be written as 8 into 1 by 8 plus, and 1 by 2 into how many phases? 6 phases, 3, that is 1 plus 3, that is equal to 4. So in case of FCC, the Z is equal to 4. Number of effective atoms, that is 4. So remember it, it is very important, number of atoms. Okay. Next we will find out some important relationship, that is relationship between nearest neighbor distance D edge length of unit cell A and the radius of sphere, and the radius of sphere. Sphere means the packing particles, the constituting particles, it may be atoms, ions or other things, and the radius of sphere, this is designated by R. Relation among, you can write over here, relation among, it's very important, this relation you should know. Okay, so first one I need to derive for simple cubic or primitive. For a simple cubic or primitive unit cell. So for a simple or primitive unit cell, you know the particles are present at the corners. You see this geometry, actually if you visualize it 3-dimensionally, so this one is one sphere and this one is another sphere. Okay, let me do. And 2 spheres are just present behind it like this, and another 2 spheres are just over the first layer like this, and here and here. You see, this is just a cube, simple or primitive. Okay, so all the 4 spheres below are just in touch with the 4 spheres above, in the below layer and above layer are connected to each other, and each spheres are connected to each other. Okay, so like this, here this is the first layer and second layer like this, and okay, so each spheres are touching to each other. So the edge length, that is the length of unit cell, edge length, here you see, if you visualize it properly, so I can write over here, this one is a simple cube. In case of simple, particles are only at the corners. You tell me now, as I have shown you, this sphere and this sphere are touching to each other, and here this distance is the length of unit cell, edge length, each side a cube, all cases that will be a. So if the radius of each sphere is smaller, then can I write a is equal to 2r? Yes, a is equal to how much? 2r. This is the relationship between the radius of sphere and your edge length. A is equal to 2r. Okay, so if I derive the radius of sphere r, that will be a by 2, or you can see 0.5 a. This is the relation. Then the second one, that is for a BCC, body centered cubic unit cell. So you just imagine, suppose these are two spheres, okay, and just below these are four spheres, three dimensional. You try to understand. If I place a sphere just at the middle, this is at this depression of first layer, then tell me, would you think the second layer, second, fourth spheres will touches this spheres? No. Rather, this sphere, they don't touch each other. They don't touch each other. Okay, there are four spheres, and another sphere you can place at the depression, and next four spheres you have to connect. So definitely these spheres don't connect to each other. Rather, these three spheres are diagonally connected to each other. That means spheres touches through diagonally. That means one at the corner, another the middle one, and another that is the at behind. So they are diagonally body diagonally connected to each other. Okay, so here you just see like this. Particles are at the corner and another one at the middle. So these three spheres are connected to each other. Body diagonally they are connected to each other. So you just think, if I join this line, this one is A, B, C. Then tell me, if this one is A, this one is A, then that will be root 2A. That means AB, that is equal to root 2 into A. Is that clear? So here, since A, this sphere and this sphere at the center and this sphere are connected to each other, so I can directly write AC, that is equal to 4R. Here are 2R and R. So that will be 4R. So that implies this AB, that is equal to root 2A. And what is the value of SC? If you compare this triangle, this is A, root 2A, that is SC. SC you can apply Pythagoras theorem, that is SC, that is equal to AB square plus BC square. So that will be root 2A whole square plus A square, that will be 2A square plus A square, root over of, so the value will be root 3 into A. Okay, so I can write over here that AC is equal to 4R, that means root 3A, that is equal to 4R. Then find out the value of R, that will be root 3 by 4 upon A. This is the expression for BCC. And the last one, that is for face centered cubic. Face centered cubic, FCC. For a FCC unit cell, what can I write over here? And here the nearest neighbor distance in case of a BCC, that is this sphere and this sphere at the center, they are touching to each other. So here the radius r plus this radius r, 2r, that will be SC by 2. So the nearest neighbor distance I can say this AE, suppose central position is E. So AE, that is the nearest neighbor distance, that is D, that is equal to SC upon 2, SC by 2. So SC by 2 means that will be equal to, SC is your root 3A by 2. This is the relationship, the nearest neighbor distance and edge length, in terms of edge length. Okay, so again R is equal to root 3 by 4A. So now for a face center, you see particles are connected face diagonally to each other. Just imagine four spheres, again four spheres are there. If you place a sphere at the center of face in case of FCC, then tell me, do you think that these spheres will connected to each other? No, rather they are connected this face diagonally to each other. Okay, so if this one is A, this one is A, so this one will be root 2A. Okay, so that root 2A is equal to 4R. Here root 2A, root 2A, that is equal to 4R. So that implies R, that is equal to root 2 by 4 into A. Is that clear? So that will be root 2 by, I can write this 4 also, 2 into root 2 into root 2, that will be 4 into a. So 1 root 2 get cancelled. So you are getting a by 2 root 2. So r is equal to a by 2 root 2 in case of your face centered cubic unit cell. Okay, so the next class we will discuss about their packing efficiency of 3 different cubic unit cells. Okay, thank you.